You are trapped in a cage you cannot see. Its bars aren't made of steel, they're made of space-time itself, and they close in at the speed of light. Every atom in your body obeys this prison. Every thought you have respects its boundaries. But what built this cage, and why does the universe guard this speed like a secret? And here is a question. If you could travel at 1 light year per second, where in the universe would you go and why? Let us know in the comments. I will pin the most creative answer. Now let's begin. To understand why light speed is the limit, we need to travel back to 1887. Two American scientists, Albert Michelson and Edward Morley, conducted what became one of the most famous experiments in physics history. They wanted to measure Earth's movement through something called the luminiferous ether, a substance people believed filled all of space and carried light waves. They set up an incredibly precise device that split a beam of light, sent it in 2 perpendicular directions, then brought the beams back together. If Earth was moving through this ether, the light traveling in the direction of Earth's motion should take longer to return than the light moving perpendicular to it. It's like swimming upstream versus across a river. But something unexpected happened. The light beams arrived at exactly the same time, no matter which direction they traveled. There was no difference whatsoever. This wasn't a small error, it was a complete absence of the effect they expected. The experiment failed to find what they were looking for, yet this failure became one of the most important results in scientific history. It told us something shocking. Light always moves at the same speed, regardless of how you're moving when you measure it. This result baffled scientists. How could light behave this way? If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing on the ground sees that ball moving at 150 kilometers per hour. You add the speeds together, that's common sense, but light doesn't follow this rule. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, you might expect that light to move at 1.5 times light speed, but it doesn't. That beam still moves at exactly the speed of light, no faster. The same speed you'd measure if you were standing still. This is where Albert Einstein enters the story. In 1905, Einstein published his theory of special relativity. He proposed something radical. The speed of light is constant for everyone, everywhere, no matter how fast they're moving. This wasn't just a quirk of light, it was a fundamental law of the universe. To make this work, Einstein realized something even stranger. Space and time are not separate, fixed things. They're connected, they can stretch and squeeze. What we call space-time is flexible, and it bends to keep the speed of light constant. Let me explain this with a thought experiment. Imagine you're on a spaceship accelerating toward a distant star. As you go faster and faster, strange things start happening. Time on your ship begins to slow down compared to time on Earth. Distances in the direction you're traveling appear to shrink. Your mass, or more accurately, your resistance to acceleration, increases. These aren't illusions, they're real physical changes happening because you're moving at a significant fraction of light speed. The faster you go, the more extreme these effects become. Now here's the crucial part. As you approach the speed of light, accelerating becomes harder and harder. It's not just that your engines aren't powerful enough, it's that the universe itself resists your acceleration. Your mass effectively increases toward infinity. To push you even 1 kilometer per hour faster would require more energy than exists in the entire cosmos. This is why nothing with mass can reach light speed. The universe simply won't allow it. But light itself has no rest mass. Photons, the particles of light, are born moving at light speed. They never accelerate, they never slow down in a vacuum. They simply exist at this cosmic boundary, traveling through the geometry of space-time itself. This is their natural state. It's not that light is special because it moves fast. It's that light reveals the speed limit built into the structure of reality. Now you might be thinking, why does the universe have this limit at all? Why not make it faster or slower? Here's where things get truly profound. The speed of light isn't just about movement, it's about causality, the order of cause and effect. Every event in the universe has a cause that comes before it. You flip a switch and a light turns on. You throw a ball and it flies through the air. Cause, then effect. This sequence is sacred to how reality functions. And the speed of light protects this order. If something could move faster than light, causality would break. Imagine you send a signal faster than light to a distant star. From your perspective, the signal arrives in the future, but according to someone moving at a high speed relative to you, that signal arrives in the past. Suddenly effects happen before their causes. Events lose their logical sequence. Time stops making sense. This isn't just confusing, it's impossible for a coherent universe to function. The speed of light acts as the guardrail preventing reality from falling into chaos. It's the absolute boundary that keeps time ordered, events consistent, and the universe understandable. Let's explore what recent science tells us about this limit. Just 2 months ago, in February 2026, an international team of researchers published a groundbreaking study in Physical Review D. They used some of the most energetic light ever detected, ultra-high energy gamma rays from distant cosmic explosions and flaring galaxies billions of light years away. These photons traveled across vast stretches of the universe before reaching our telescopes. The scientists were testing something extraordinary. Does light at extremely high energies travel at a slightly different speed than lower energy light? Some theories of quantum gravity suggest that spacetime might have a grainy quantum texture at incredibly tiny scales. If this is true, high-energy photons might interact with this texture differently, arriving at Earth just a tiny bit earlier or later than lower-energy ones. Even a difference of a trillionth of a second over billions of years would reveal new physics beyond Einstein's relativity. The researchers analyzed gamma rays from sources so distant that their light began its journey when the universe was much younger. They measured arrival times with extraordinary precision, searching for any hint that Einstein's cosmic speed limit might crack under extreme conditions. What did they find? Nothing. Absolutely nothing. The high-energy photons and low-energy photons arrived exactly when Einstein's theory predicted they would. There was no variation, no crack in the foundation. The speed of light remained constant, even under the most punishing cosmic stress test humans have ever devised. In fact, this study tightened the constraints on potential deviations by a factor of 10 compared to previous measurements. If new physics exists beyond relativity, it's hidden far deeper than many theories suggested. This isn't the only recent test. In November 2025, researchers from the Institute of Space Studies of Catalonia and the Universitat Autònoma de Barcelona, working with colleagues in Portugal, published similar findings. They used observations from the MAGIC telescopes, which detect very high-energy gamma rays. These instruments are so sensitive they can spot the faint flashes of light created when gamma rays slam into Earth's atmosphere. By analyzing these gamma rays from distant sources, the team demonstrated with unprecedented accuracy that the speed of light does not depend on photon energy. Their results increased the precision limit tenfold, further cementing Einstein's theory as one of the most rigorously tested ideas in all of science. But here's what's beautiful about science. We keep testing, we push the boundaries, we ask uncomfortable questions. Even though Einstein's speed limit has survived every challenge for over a century, physicists continue probing for exceptions. Why? Because discovering even the tiniest deviation would revolutionize our understanding of reality. It could help us unify general relativity with quantum mechanics, two theories that work brilliantly on their own but clash when brought together. It could reveal the quantum nature of space-time itself. It could open pathways to technologies and ideas we can't yet imagine. Think about what this means for our place in the cosmos. The speed of light limit isn't just a technical detail for physicists. It shapes the universe we experience. It determines how far we can see, how fast we can communicate, and ultimately, how connected we are to distant parts of the cosmos. When you look up at the night sky, you're seeing the past. The light from the nearest star beyond our Sun, Proxima Centauri, takes about 4 years to reach us. We see it as it was 4 years ago. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. When you gaze at Andromeda, you're seeing light that began its journey when our ancestors were just learning to use stone tools. This cosmic speed limit creates a kind of horizon. There are regions of the universe so far away that their light will never reach us. The universe is expanding, and in the most distant reaches, space itself is stretching faster than light can travel through it. These regions are beyond our cosmic horizon, forever unreachable, forever unknowable. The speed of light doesn't just limit how fast we can go, it limits what we can ever observe, what we can ever know about the universe. If you're finding this journey through the cosmos fascinating, please hit that subscribe button and give this video a thumbs up. It helps this channel grow and allows me to create more content exploring the deepest mysteries of the universe. Your support truly makes a difference. Let's dig deeper into why mass makes such a difference. Remember, light can travel at light speed because photons have no rest mass. But you, me, every atom in our bodies, we have mass. And mass changes everything. In Einstein's framework, energy and mass are connected through his famous equation, E equals mc squared. This tells us that mass is a form of concentrated energy, but there's more to the story. As you accelerate, your kinetic energy increases. And here's the twist, that additional energy contributes to your inertia, your resistance to further acceleration. The faster you go, the more energy you have, and the more that energy resists going even faster. Imagine pushing a shopping cart. At first, it's easy. A gentle push gets it rolling, but now imagine that with every meter the cart moves, it becomes heavier. Not just a little heavier, exponentially heavier. By the time it's moving at half its maximum speed, it weighs twice as much as when you started. At 3/4 speed, it weighs 4 times as much. As it approaches its maximum speed, its weight approaches infinity. No matter how hard you push, no matter how much energy you pour into it, you can never quite reach that final limit. This is what happens to any object with mass as it approaches light speed. The universe itself makes the object harder and harder to accelerate. Physicists describe this with something called the Lorentz factor. At everyday speeds, walking, driving, even flying in a jet, this factor is almost exactly 1. Time dilation, negligible, length contraction, unnoticeable. But as you approach light speed, the Lorentz factor shoots toward infinity. At 90% light speed, time for you runs about 44% slower than for someone at rest. At 99%, it's about 7 times slower. At 99.9%, about 22 times slower. The closer you get to light speed, the more extreme these effects become, approaching infinity as you approach the ultimate limit. Scientists have verified these effects countless times. Particles in accelerators like the Large Hadron Collider routinely reach 99.9999% of light speed. At these velocities, the particles live far longer than they would at rest because time for them slows down dramatically. We can measure this, we can calculate it. The predictions match observations with stunning precision. Cosmic rays, high-energy particles from space, smash into Earth's atmosphere and create showers of secondary particles called muons. These muons normally decay in about 2 microseconds, but because they're moving so fast, time dilation extends their lifetime enough that they reach the ground before decaying. Without relativity, they'd vanish long before reaching sea level. The fact that we detect them is direct proof that time really does slow down at high speeds. Here's another astonishing consequence. Simultaneity breaks down. Events that appear simultaneous to you might not appear simultaneous to someone moving at a different speed. Imagine 2 lightning bolts strike the front and back of a moving train at the same instant, as measured by someone standing on the platform. But for someone on the train moving toward one strike and away from the other, the strikes don't happen at the same time. This isn't an illusion or a measurement error, it's a fundamental feature of spacetime. There is no universal now that everyone agrees on. Time is relative, woven together with space into a 4-dimensional fabric that bends and flexes depending on your motion and position in a gravitational field. This brings us to one of the most mind-bending aspects of the speed limit, its connection to the very structure of spacetime. Einstein didn't just discover that light speed is constant, he revealed that space and time are not separate stages where events happen. They're part of a unified entity, a 4-dimensional continuum, where every event has coordinates in both space and time. You can't move through space without also moving through time. In fact, physicists describe motion through space-time as something everything does constantly. Even when you're sitting perfectly still in space, you're moving through time at maximum speed. When you start moving through space, some of your motion through time converts to motion through space. The faster you move through space, the slower you move through time. Light moving at the cosmic speed limit through space doesn't experience time at all. From a photon's perspective, if it could have one, its journey from a distant galaxy to your eye happens instantaneously. Think about that for a moment. A photon emitted from a star 13 billion light-years away travels for 13 billion years from our perspective, but from the photon's perspective, no time passes. It's emitted and absorbed in the same instant. This reveals something profound about the nature of light and the geometry of space-time. Light doesn't travel through space-time the way matter does. It traces what physicists call null geodesics, pathways along the very edge of the possible where space and time balance perfectly. Now let's address something you might be wondering. What about quantum entanglement? You may have heard that when 2 particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Doesn't this violate the speed limit? It's a great question, and the answer reveals just how subtle and clever the universe is. Entanglement does create correlations between particles that seem to happen instantaneously across any distance. But here's the crucial point. You cannot use entanglement to send information faster than light. When you measure one particle, you get a random result. The other particle's measurement will be correlated with yours, but neither of you knows what the other measured until you compare notes using conventional, slower-than-light communication. The speed limit isn't about how fast correlations can exist. It's about how fast information, causality, and influence can travel. And entanglement, strange as it is, respects this boundary. The universe protects its speed limit in remarkably clever ways. Every time we think we've found a loophole, nature closes it. What about wormholes, those hypothetical tunnels through space-time that could connect distant regions? Science fiction loves them, and general relativity does allow their mathematical possibility. But creating a stable, traversable wormhole would require exotic matter with negative energy density, something we've never observed and may not exist in the quantities needed. Even if wormholes exist, they don't violate causality. You're not moving faster than light through space, you're taking a shortcut through a different geometry of space-time itself. It's like folding a piece of paper to bring two distant points together. You're not exceeding the speed limit, you're changing the playing field. What about the expansion of space itself? The universe is expanding and distant galaxies are moving away from us. In fact, galaxies beyond a certain distance are receding faster than light. Doesn't this break the rule? Again, the universe is more subtle than it first appears. Space itself can expand at any rate. There's no speed limit on the expansion of space-time. What the speed limit constrains is local motion through space. A galaxy far away isn't moving through space faster than light. Space between us and that galaxy is stretching. The galaxy remains stationary in its local patch of space-time, obeying all the rules. We simply can't see beyond a certain distance because the space between us and those regions is expanding too fast for light to ever bridge the gap. This creates what we call the cosmic horizon, the boundary of the observable universe. Recent observations from missions like the James Webb Space Telescope continue to deepen our understanding of this cosmic expansion. Launched on December 25, 2021, this incredible instrument peers deeper into the universe than ever before. It observes galaxies that formed just a few 100 million years after the Big Bang, when the universe was only a fraction of its current age. The light from these galaxies has been traveling for over 13 billion years. During that journey, space itself has expanded dramatically. The galaxies that emitted this light are now much farther away than 13 billion light-years because space has stretched while the light was in transit. Webb doesn't violate the speed limit by seeing these distant objects. It simply collects the ancient light that has finally completed its long journey across expanding space. Let's talk about what happens at the extreme edges of physics, where the speed limit becomes a matter of survival for reality itself. In the cores of neutron stars, matter is compressed to densities where a sugar cube-sized chunk would weigh as much as all of humanity. Here, gravity is so intense that space-time curves dramatically. Light trying to escape from near the surface gets redshifted, losing energy as it climbs out of the gravity well. But even here, even in these extreme environments where the fabric of space-time warps severely, light still travels locally at the same speed. The path it takes curves because space-time curves, but the speed remains constant. Black holes take this to the ultimate extreme. At the event horizon, the boundary of no return, space-time curves so severely that all future paths point inward. Once you cross this threshold, every direction you can move leads toward the singularity at the center. You can't escape not because you can't move fast enough, but because the geometry of space-time itself forbids outward paths. Even light moving at the cosmic speed limit cannot escape. The event horizon isn't a physical barrier, it's a geometric point of no return, a place where the structure of space-time makes leaving impossible. Scientists continue to probe black holes with increasing sophistication. The Event Horizon Telescope, a network of radio telescopes spanning the globe, captured the first direct image of a black hole's shadow in April 2019. The target was the supermassive black hole at the center of the galaxy Messier 87, located about 55 million light-years away. In May 2022, they revealed an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. These images don't show the black holes themselves. Nothing can escape from inside the event horizon, not even light. They show the glowing ring of superheated gas swirling around the black hole, light bent by the extreme curvature of space-time. These observations confirm Einstein's predictions with remarkable precision. The speed of light, even in these monstrous gravity wells, remains the fundamental constant holding reality together. Here's something that might surprise you. The speed limit also determines the maximum rate at which information can spread through the universe. Information, in the physics sense, isn't just data on a computer. It's any change in physical state that can be measured or observed. When you flip a light switch, information travels from the switch to the bulb at the speed of electricity through the wire, which is a significant fraction of light speed. When you speak, sound waves carry information through air at about 343 meters per second, but the absolute maximum rate at which any information, any causal influence can propagate is the speed of light. This creates what physicists call the light cone, a geometric representation of all the events that could possibly be influenced by or influence a given point in space-time. Imagine you're standing at a specific location at a specific moment. Draw a cone expanding outward from that point at the speed of light. Everything inside that cone represents events that can causally affect you or be affected by you. Everything outside is causally disconnected, at least for now. As time passes, your light cone expands, encompassing more of the universe, but there will always be regions beyond your reach, events that cannot influence you and that you cannot influence. This isn't just a theoretical limitation. It's a fundamental feature of how cause and effect work in our universe. The speed limit enforces the boundaries of what's possible, but what actually happens if we reach light speed? Check out the video on the card above to find out. That video dives deep into the bizarre consequences of approaching this cosmic boundary, from time dilation to length contraction, and what the universe would look like if you could ride a beam of light. Let's consider the cosmic implications of this speed limit for our understanding of the universe's history. The Big Bang, the moment when our universe began expanding from an incredibly hot, dense state, occurred approximately 13.8 billion years ago. This means the farthest we can possibly see is about 13.8 billion light-years in travel time. But remember, space has been expanding during that journey. The actual distance to the most distant observable objects is much greater, about 46 billion light-years in what's called co-moving distance. Beyond this cosmic horizon lies a realm we can never observe, not because our telescopes aren't powerful enough, but because light from those regions hasn't had time to reach us yet. The speed limit literally defines the boundaries of the observable universe. This creates a humbling perspective. When we talk about the universe, we really mean the observable universe, the bubble of space-time within our cosmic horizon. What lies beyond? We don't know. It could be more of the same, galaxies and stars continuing infinitely in all directions. It could be something entirely different. Some theories suggest a multiverse, countless bubble universes beyond our own, each potentially with different physical laws. But the speed limit prevents us from ever directly observing these regions. Our knowledge is bounded by the distance light can travel in the age of the universe. Here's where it gets even more interesting. The universe isn't just expanding, it's accelerating. Back in 1998, two independent teams of astronomers made a shocking discovery. They were studying distant supernovae, exploding stars that serve as cosmic distance markers, expecting to find that the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The expansion is speeding up. Some mysterious force, which we call dark energy, is pushing the universe to expand faster and faster. This discovery earned the researchers the Nobel Prize in Physics in 2011, and it fundamentally changed our understanding of the cosmos. What does accelerating expansion mean for the cosmic speed limit? It means that our observable universe will actually shrink over cosmic time. Right now, we can see galaxies billions of light-years away, but as space expands faster and faster, distant galaxies will recede beyond our cosmic horizon. Their light will become so redshifted that it fades into invisibility. Eventually, trillions of years in the future, If the acceleration continues, galaxies outside our local group will disappear from view. Future astronomers in that distant era will look up and see a much emptier universe, not because galaxies have vanished, but because the expansion of space has carried them beyond the reach of light itself. The speed limit, combined with cosmic expansion, determines not just what we can see now, but what anyone will ever be able to see. Let's return to the quantum world for a moment, because the speed of light shows up in surprising places there too. In quantum field theory, the mathematical framework that describes how particles and forces work at the smallest scales, the speed of light isn't just about photons, it's a fundamental parameter built into the structure of reality. Every particle, every field, every interaction respects this limit. When particle physicists calculate how particles interact, the speed of light appears in their equations as a conversion factor between space and time, between energy and momentum. It's woven into the fabric of quantum reality just as deeply as it is in relativity. One of the most remarkable confirmations of this came from neutrino observations. Neutrinos are ghostly particles with almost no mass that barely interact with matter. Trillions of them pass through your body every second from the sun and you never notice. In 1987, astronomers detected neutrinos from a supernova explosion in the Large Magellanic Cloud, a small galaxy about 168,000 light-years away. The neutrinos arrived at Earth within hours of the light from the same explosion. This timing confirmed that neutrinos, even though they have a tiny mass, travel at very close to the speed of light. More importantly, it confirmed that the speed limit applies across vast cosmic distances and to different types of particles. The universe plays by consistent rules. More recently, in February 2026, researchers used the Neutrino Telescope to analyze one of the highest energy neutrinos ever detected, dubbed KM3. This neutrino carried an estimated energy of 220 peta-electron-volts, with uncertainty ranging from 110 to 790 peta-electron-volts. If it came from an extragalactic source, as scientists suspect, its arrival time allowed researchers to test whether neutrinos moving at such extreme energies might travel faster than light. Once again, the results showed no violation. The neutrino arrived precisely when relativity predicted it should. Even at energies we can barely comprehend, the cosmic speed limit holds firm. This consistency is what makes physics so powerful. The same laws that govern particles in a laboratory on Earth also govern particles crossing billions of light-years of space. The speed of light measured in a basement at a university is the same speed measured in the heart of a quasar billions of light-years away. This universality isn't something we can take for granted. It's a profound feature of our cosmos that the laws of physics are the same everywhere and at all times. Without this consistency, science itself would be impossible. We couldn't make predictions, we couldn't understand distant objects. The fact that we can measure the speed of light here and trust that it's the same everywhere is one of the deepest and most beautiful truths about reality. Let's explore what this means for practical technology. Engineers designing GPS satellites must account for relativistic effects. These satellites orbit Earth at about 14,000 kilometers per hour, much slower than light but fast enough that relativity matters. Additionally, they're farther from Earth's gravitational pull, which also affects time according to general relativity. Combining these effects, clocks on GPS satellites run slightly faster than clocks on the ground, gaining about 38 microseconds per day. This might sound trivial, but light travels about 300 meters in 1 microsecond. Without correcting for relativity, GPS positions would drift by kilometers per day. Every time you use navigation on your phone, you're relying on Einstein's theories and the constancy of the speed of light. The cosmic speed limit isn't just abstract physics, it's technology you use every day. particle accelerators provide another stunning application. At CERN's Large Hadron Collider, protons race around a 27-kilometer ring at 99.99999% the speed of light. At this velocity, time for the protons slows down by a factor of about 7,000. They complete 11,000 laps per second, experiencing relativistic effects so extreme that engineers must carefully account for them. The magnet steering the protons must be precisely calibrated because the proton's effective mass increases by that same factor of 7,000. If engineers ignored relativity, the beams would crash into the walls immediately. Instead, by embracing Einstein's framework, physicists smash these protons together at energies high enough to recreate conditions that existed fractions of a second after the Big Bang. Every collision confirms that the speed limit holds, even at energies that dwarf anything found naturally on Earth. Now here's a question that captures the imagination. Could we ever find a way around the speed limit? Science fiction is filled with ideas: warp drives, hyperspace, tachyons. Are any of these possible? Let's examine them through the lens of real physics. A warp drive, as popularized by Star Trek, was actually given a mathematical foundation by physicist Miguel Alcubierre in 1994. His solution to Einstein's field equations describes a bubble of space-time that contracts space in front of a ship and expands it behind. The ship itself doesn't move through space faster than light. Space moves around the ship. It's a brilliant idea that technically doesn't violate relativity because nothing is moving through local space faster than light. But there's a massive catch, several actually. The Alcubierre drive requires exotic matter with negative energy density, something we've never observed in the quantities needed. Some estimates suggest you'd need more negative energy than the total positive energy in the observable universe. Even if such matter exists, there are causality problems. A ship using a warp drive could potentially create closed time-like curves, paths through space-time that loop back to the past, allowing time travel paradoxes. The universe seems to conspire against this. Every time we find a mathematical loophole in relativity, additional physics constraints slam the door shut. It's as if the cosmos is deeply committed to protecting causality and the speed limit. Tachyons are hypothetical particles that always move faster than light. If they exist, they would have imaginary mass, a mathematical property that makes them fundamentally strange. But here's the problem. We've never detected a tachyon, and their existence would create severe causality violations. If tachyons exist, you could use them to send messages to your own past, creating paradoxes. Most physicists believe tachyons don't exist precisely because they would break the logical consistency of the universe. The speed limit isn't just a rule about motion. It's a safeguard for reality itself. What about quantum tunneling? In the quantum world, particles can sometimes pass through barriers they classically shouldn't be able to cross. They tunnel through. Some experiments have shown particles appearing on the other side of a barrier seemingly faster than light would take to cross that distance. Does this violate the speed limit? The answer is subtle. While the particle does appear on the other side quickly, no information travels faster than light. The leading edge of the particle's probability wave was already on the other side before tunneling occurred, and you can't use tunneling to send a signal faster than light. Once again, the universe protects the speed limit with remarkable cleverness. This brings us to one of the deepest questions in modern physics. Why is the speed of light the specific value it is? Why approximately 300,000 kilometers per second and not some other number? The truth is, we don't fully know. In physics, we have many fundamental constants: the gravitational constant, the charge of an electron, Planck's constant. These numbers seem arbitrary. They're not derived from deeper principles. They're measured through experiments. The speed of light is one of these fundamental constants. In fact, Since 1983, we've defined the meter in terms of the speed of light rather than the other way around. 1 meter is the distance light travels in exactly 1,299,792,458 of a second. We've essentially fixed the speed of light by definition and use it to define distance. But this just rephrases the question. Why does the universe have the structure it does, where this particular speed serves as the cosmic limit? Some physicists speculate that in other universes, if they exist, the speed limit might be different. Perhaps in some bubble universe, light moves 1,000,000 times faster. Perhaps in another, it's much slower. Our universe happens to have this particular value, and we exist to observe it because if it were too different, the physics necessary for stars, planets, and life might not work. This is a version of the anthropic principle. We observe the constants we do because we couldn't exist in a universe with wildly different values. There's a beautiful connection here between the very large and the very small. The speed of light links cosmology, the study of the entire universe, with quantum mechanics, the physics of the tiniest particles. When we observe the cosmic microwave background, the afterglow of the Big Bang, we're seeing light that has traveled for over 13 billion years. This light carries information about the quantum fluctuations that existed in the first moments after the Big Bang, tiny ripples that grew into galaxies and galaxy clusters. The speed limit determined how fast those fluctuations could grow, how information could spread through the early universe, and ultimately, how structure formed. You, me, Earth, the Sun, we're all here because the universe has a speed limit that allowed matter to clump together over billions of years. Let's consider the psychological and philosophical implications. The speed limit means the universe has a horizon beyond which we cannot see or influence anything. This creates a fundamental limit to knowledge. There are questions we might want to answer. What's happening right now in a galaxy 10 billion light-years away that have no meaningful answer? Right now isn't well defined across such vast distances. Simultaneity is relative. The speed limit forces us to accept that reality is more subtle, more interconnected than our everyday intuition suggests. Space and time aren't separate stages. They're woven together. What's now for you isn't now for someone moving at a different velocity. This is deeply strange, yet it's how the universe actually works. Here's something that might blow your mind. Because of the speed limit and the expansion of space, there are galaxies we can see right now whose light will never reach us again if we wait. They're already receding faster than light due to cosmic expansion. We're seeing their ancient light, emitted billions of years ago when they were closer, but any light they emit today will never catch up to us. Space is expanding too fast. We're seeing ghosts, images of galaxies that are, in a sense, already beyond our cosmic horizon. The speed limit creates a universe where the past is visible, but the present and future of distant regions are hidden forever. This creates a poignant beauty. We're living in a special cosmic era where we can still see a rich, galaxy-filled universe. Trillions of years from now, if intelligent beings exist in our galaxy or local group, they'll look up and see far fewer galaxies. They'll observe a lonelier universe, not because galaxies have died, but because space has carried them beyond the reach of light. The speed limit combined with cosmic expansion means the universe we observe is transient. We're privileged to live in an age where the cosmos is still richly observable. This makes our moment in cosmic history precious. Let's bring this back to us, to humanity, to you. You are made of atoms forged in the cores of ancient stars. Carbon, oxygen, nitrogen, iron. Every heavy element in your body was created by nuclear fusion or supernova explosions billions of years ago. Those atoms, scattered across space, eventually condensing into the molecular cloud that formed our sun and planets. You literally are stardust, rearranged into a form capable of contemplating the cosmos. And the speed limit, this fundamental law of the universe, governs every interaction of every particle in your body. When electrical signals travel along your nerves, they propagate at a fraction of light speed. When you see photons traveling at the cosmic speed limit enter your eyes and interact with molecules in your retina, you are, in every sense, a manifestual expression of the laws of physics, including the cosmic speed limit. The fact that you can understand these concepts, that your brain, a collection of atoms governed by quantum mechanics and relativity, can comprehend the structure of spacetime, is perhaps the most astonishing thing of all. We are the universe becoming aware of itself, asking questions about its own nature. The speed limit isn't just an abstract rule, it's part of the framework that makes your existence possible. Now let's explore some of the cutting-edge research that's pushing our understanding even further. Scientists are currently investigating whether the speed of light might have been different in the early universe. Some cosmological models suggest that in the first tiny fractions of a second after the Big Bang, physical constants might have varied. If the speed of light was different during this primordial era, it could help explain certain puzzles in cosmology, like the horizon problem. Why distant regions of the universe that couldn't have communicated with each other have the same temperature. The European Space Agency's Gaia mission, launched in December 2013, is mapping the positions and movements of over 1 billion stars in our galaxy with unprecedented precision. While Gaia's primary mission is creating a three-dimensional map of the Milky Way, its data also allows scientists to test relativity in new ways. By observing how starlight bends around massive objects, by measuring tiny relativistic effects on stellar positions, Gaia is essentially testing whether the speed of light and the structure of spacetime behave exactly as Einstein predicted. So far, every measurement confirms the theory. The Laser Interferometer, gravitational wave observatory known as LIGO, opened an entirely new window on the universe when it detected gravitational waves for the first time in September 2015. These ripples in spacetime itself, predicted by Einstein a century earlier, travel at exactly the speed of light. When two black holes or neutron stars spiral together and merge, they send gravitational waves racing across the cosmos. LIGO and its partner, Observatory Virgo, have now detected dozens of these events. Each detection confirms that gravitational waves propagate at light speed, exactly as general relativity predicts. This is remarkable because gravitational waves are fundamentally different from electromagnetic waves. They're distortions in the fabric of spacetime itself, yet they obey the same cosmic speed limit. In August 2017, LIGO and Virgo detected gravitational waves from two neutron stars colliding. Within seconds, telescopes around the world observed light from the same event. The gravitational waves and light arrived at Earth within about 2 seconds of each other after traveling for 130 million years. This extraordinary observation showed that gravitational waves and light travel at the same speed to an accuracy better than 1 part in a quadrillion. If gravity propagated even slightly faster or slower than light, we would have noticed. The universe is telling us loudly and clearly that there's a universal speed limit that applies to all fundamental interactions, not just light. What about attempts to slow down or speed up light? Interestingly, scientists can manipulate the speed of light in certain materials. When light travels through glass or water, it slows down. This is why lenses can focus light and why objects underwater appear bent. The slowdown happens because photons interact with the atoms in the material. In some exotic experiments, physicists have slowed light to mere meters per second by passing it through ultra-cold atomic clouds. They've even briefly stopped light completely, storing its information in atomic states, then releasing it again. Does this violate the cosmic speed limit? Not at all. The fundamental speed limit is about the speed of light in vacuum. In materials, light can travel slower, but it can never exceed the vacuum speed. The cosmic speed limit remains absolute. There's also been research into materials with negative refractive indices, exotic metamaterials engineered at the nanoscale. In these materials, light behaves in bizarre ways, bending backward, for example. But even here, no information travels faster than the vacuum speed of light. The phase velocity of light waves might exceed light speed in certain situations, but the group velocity, the speed at which information or energy propagates, always respects the limit. The universe has multiple layers of protection ensuring that causality cannot be violated. Let's talk about the cosmic microwave background again, because it offers another stunning confirmation of the speed limit. This faint glow fills the entire sky, light from approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to stream freely. Missions like COBE in the 1990s, WMAP in the 2000s, and Planck in the 2010s mapped this radiation with exquisite precision. The patterns in the cosmic microwave background reflect sound waves, yes, sound waves, propagating through the hot plasma of the early universe. These acoustic oscillations had a maximum speed determined by the speed of light and the density of matter and energy. By analyzing the pattern of hot and cold spots in the cosmic microwave background, cosmologists can measure fundamental properties of the universe, including how the speed limit shaped the early cosmos. The beautiful thing is that all these independent lines of evidence, particle accelerators, GPS satellites, gravitational wave detectors, cosmic ray observations, gamma-ray telescopes, cosmological measurements, all point to the same conclusion. The speed of light is constant. It's the same in all reference frames. It's the maximum speed for information and causality. This convergence of evidence from wildly different domains is what makes the speed limit one of the most solid foundations in all of science. Now, I want to address a common misconception. People sometimes think that relativity is just a theory, implying it's uncertain or unproven. In science, a theory doesn't mean a guess. It means a comprehensive framework that explains observations, makes predictions, and has been tested extensively. Relativity is a theory in the same way that gravity is a theory or that germs causing disease is a theory. It's not speculation. It's our best description of how reality works, confirmed by over a century of experiments and observations. When scientists say the speed of light is the cosmic limit, they're not guessing. They're summarizing an enormous body of evidence that all points in the same direction. But here's what's exciting. Science is never truly finished. We keep testing, keep probing, keep looking for places where our theories might break down. This isn't because we doubt relativity, it's because the edge of current knowledge is where new discoveries happen. If we ever found a genuine violation of the speed limit, it would be the most important discovery in physics in over a century. It would point toward new physics beyond Einstein, a deeper theory that includes relativity as a special case, the way relativity includes Newton's physics as a special case for slow speeds and weak gravity. Some of the most exciting potential discoveries involve the interface between quantum mechanics and general relativity. These two pillars of modern physics work beautifully in their respective domains, but clash when we try to combine them. Quantum mechanics describes the probabilistic behavior of particles at tiny scales. General relativity describes the curvature of spacetime caused by mass and energy at large scales. But what happens at the Planck scale, where both quantum effects and gravitational effects become important? This is the realm of quantum gravity, and we don't yet have a complete theory. String theory is one candidate. It proposes that fundamental particles aren't point-like, but tiny, vibrating strings. Different vibration patterns correspond to different particles. String theory naturally includes gravity and might unify all forces and particles into one framework. But string theory requires extra dimensions beyond the 3 of space and 1 of time we experience. These extra dimensions would be curled up at incredibly tiny scales. Testing string theory is extraordinarily difficult because the relevant scales are far beyond current experimental reach. And importantly, string theory respects the cosmic speed limit. Even in this exotic framework, causality and the maximum propagation speed remain central. Loop quantum gravity is another approach to quantum gravity. Instead of strings, it focuses on the fabric of spacetime itself, proposing that space is not infinitely divisible, but has a discrete structure at the Planck scale. Imagine spacetime as a woven fabric rather than a smooth continuum. At everyday scales, it appears smooth, just like a piece of cloth looks smooth from a distance. But zoom in far enough and you'd see individual threads, quantum units of space and time. Loop quantum gravity suggests that spacetime itself is quantized, made of tiny, discrete chunks. Even in this framework, the speed of light remains fundamental. It's built into the geometry of these quantum loops, into the very structure of how spacetime connects to itself. What both approaches share is respect for the cosmic speed limit. No matter how exotic the physics, no matter how strange the proposed structure of reality at the deepest levels, causality must be preserved. Information cannot travel faster than light. This isn't just a law that happens to be true. It appears to be a deep principle that any consistent theory of reality must respect. The speed limit isn't just about light, or even about motion. It's about the logical structure of cause and effect, about the coherence of reality itself. Here's a fascinating implication. The speed limit creates what physicists call the light barrier, but there's also an information barrier. Because no signal can travel faster than light, there's a maximum rate at which computation can occur, a maximum density of information that can exist in a given volume of space. These limits are related to black hole physics and entropy. Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizons, not their volume. This was shocking because it suggested that the maximum information content of a region of space is determined by its surface area, not its volume. This idea, called the holographic principle, suggests that our three-dimensional reality might be encoded on a two-dimensional boundary, like a hologram. The speed of light plays a crucial role here. The ultimate limit on information density is the Bekenstein bound, which depends on the speed of light. Cram too much information into too small a space, and you create a black hole. The speed limit, combined with quantum mechanics and gravity, determines the maximum information density possible in our universe. This connects the cosmic speed limit to information theory, thermodynamics, and even the nature of consciousness. Your brain, processing information through neural signals that travel slower than light, is constrained by these fundamental limits. Every thought you have, every computation performed by any system in the universe operates within boundaries set by the speed of light. Let's consider the practical implications for future space exploration. Humanity's most distant spacecraft, Voyager 1, launched in 1977, is now over 24 billion kilometers from Earth in interstellar space. Radio signals traveling at light speed take about 22 hours to reach it. If we sent a command to Voyager 1 right now, we'd wait 22 hours for it to arrive, and another 22 hours for confirmation, 44 hours round trip. This communication lag is a direct consequence of the cosmic speed limit. As we venture farther into space, this lag will only increase. The nearest star system, Alpha Centauri, is about 4.37 light-years away. If we sent a spacecraft there, even at a substantial fraction of light speed, say 10%, which would be an extraordinary technological achievement, the journey would take over 40 years. Radio communication with the spacecraft would take 4.37 years each way. A message sent from Earth asking, "How's it going?" would receive a response nearly 9 years later. This isn't a technological limitation we can engineer around. It's the fundamental structure of spacetime asserting itself. This creates profound challenges for interstellar civilization. Science fiction often imagines galactic empires with instant communication, but physics says otherwise. Any civilization spanning multiple star systems would be fragmented by light-speed lag. Political unity across light years would be nearly impossible. A crisis on a colony 100 light years away would be ancient history by the time word reached home. The cosmic speed limit doesn't just constrain travel, it shapes the very possibility of interstellar culture and governance. But here's an inspiring thought. These limitations also create opportunities for local autonomy and diversity. Distant human colonies would necessarily develop their own cultures, their own solutions to problems, their own evolutionary paths. The speed limit ensures that the universe will always have frontiers, always have unexplored regions, always have mysteries beyond our immediate reach. In a universe with instant communication and travel, everything would be accessible, knowable, controllable. The cosmic speed limit preserves wonder. Recent developments in propulsion technology show both progress and the enduring challenge of the speed limit. NASA's Parker Solar Probe, launched in 2018, is now the fastest human-made object ever, reaching speeds of about 700,000 kilometers per hour as it dives close to the Sun. That sounds incredibly fast, but it's only about 0.64% the speed of light. To reach even 1% of light speed would require over 15 times more velocity. And remember, as you approach light speed, energy requirements increase dramatically. The Parker Solar Probe's speed comes mainly from gravitational assists, not onboard propulsion. Achieving even a modest fraction of light speed for interstellar travel remains far beyond current technology. Breakthrough Starshot, an initiative announced in 2016, proposes using powerful laser arrays to propel tiny spacecraft with light sails to 20% of light speed. The idea is to send swarms of chip-sized probes to Alpha Centauri, arriving in about 20 years. This is theoretically possible because the spacecraft would be accelerated by light itself, photons from Earth-based lasers pushing against ultra-thin reflective sails. Even here, the speed limit asserts itself. The probes would never exceed light speed. They'd cruise at 20% of it, still taking over 2 decades to reach our nearest stellar neighbor. And because they'd be so small and fast, they'd have only minutes to gather data as they zipped through the Alpha Centauri system. They couldn't slow down. Stopping would require as much energy as accelerating. These practical challenges illustrate why the speed limit matters not just for fundamental physics, but for the future of humanity. If we're to become a spacefaring civilization, we must work within the constraints of relativity. We can't wish away the speed limit. We must design our missions, our communication systems, our social structures around it. This is what makes physics so powerful. It tells us what's possible and what's not, guiding our ambitions with reality. Let's return once more to the deepest question. What is light speed really? We've talked about it as a speed limit, as a constant, as a conversion factor between space and time, but perhaps the most profound way to understand it is as the speed of causality itself. It's the speed at which cause and effect propagate through the universe. When you flip a switch, the electromagnetic signal travels through the wire at close to light speed. When the sun emits light, that light takes about 8 minutes and 20 seconds to reach Earth. If the sun suddenly vanished, we wouldn't know for 8 minutes and 20 seconds. Not just the light, Earth would continue orbiting the now absent sun for 8 minutes and 20 seconds until the gravitational change propagated to us at light speed. This is what the speed limit really means. Causality has a maximum speed. Changes in the universe propagate outward at light speed, not instantaneously. This creates the structure of space-time, the light cones that define what can influence what. It's why the future is unknown and the past is fixed. It's why time has an arrow. The cosmic speed limit isn't just a fact about light. It's a fact about the architecture of reality, about how events connect to each other, about the very possibility of a coherent universe where cause precedes effect. Einstein didn't just discover that light speed is constant, he discovered that the universe has a fundamental structure where space and time are interwoven, where simultaneity is relative, where the cosmic speed limit governs the flow of information and causality. This structure is beautiful, strange, and utterly confirmed by over a century of observation. Every time we test it, nature agrees. The speed limit stands as one of the most certain facts we know about reality, and yet we keep exploring. The James Webb Space Telescope peers deeper into the cosmos than ever before, observing galaxies from when the universe was only a few 100 million years old. The light from these ancient galaxies has been traveling for over 13 billion years, stretched and reddened by cosmic expansion. Every photon that enters Webb's mirrors is a messenger that has journeyed across vast reaches of space-time, never exceeding the cosmic speed limit, carrying information about conditions in the early universe. These observations are testing our cosmological models, refining our understanding of how galaxies formed, how stars ignited, how the elements were forged. And underlying every measurement is the constancy of the speed of light. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the world's largest radio telescope when completed. It will observe radio waves from the early universe, detect pulsars with extraordinary precision, and search for signs of cosmic events across billions of light years. Radio waves are just another form of light, electromagnetic radiation with longer wavelengths than visible light, and they too travel at the cosmic speed limit. The SKA will essentially be a time machine looking backward through cosmic history, limited in how far it can see by the finite age of the universe and the speed of light. Closer to home, experiments at the quantum frontier continue to probe the limits of what's possible. Quantum computers are being developed that could potentially solve certain problems exponentially faster than classical computers. But even quantum computers respect the cosmic speed limit. Quantum entanglement, that spooky correlation between particles, cannot be used to send information faster than light. The no-communication theorem in quantum mechanics proves this rigorously. Every time physicists think they've found a loophole, a deeper analysis shows that causality is protected. The universe seems almost cleverly designed to prevent violations of the speed limit. The search for dark matter and dark energy also connects to the cosmic speed limit. Dark matter, which makes up about 27% of the universe's mass energy, doesn't emit light, but it interacts gravitationally. Its presence is inferred from the motion of galaxies and the bending of light around galaxy clusters. Dark energy, making up about 68% of the universe, drives cosmic acceleration. Both are mysteries, but whatever they are, they must respect relativistic physics. Dark matter particles, if they exist, cannot travel faster than light. Dark energy's effects propagate at light speed. Even the unknown components of the universe obey the cosmic speed limit. This brings us to a humbling realization. We understand only about 5% of the universe, the ordinary matter made of atoms. The rest is dark matter and dark energy, mysterious components we've detected only through their gravitational effects. Yet even in our ignorance, we know that whatever dark matter and dark energy are, they must fit within the framework of relativity. The cosmic speed limit constrains even what we don't understand. This is the power of fundamental principles. They guide us even into unknown territory. Let's think about the philosophical implications one more time. The speed limit creates a universe where not everything is knowable, where exploration remains meaningful, where the future is genuinely open. If we could see or influence distant regions instantaneously, the universe would be deterministic in a much more absolute sense. The speed limit creates space, literally, for events to unfold independently, for different regions to evolve separately, for genuine novelty to emerge. In a sense, the cosmic speed limit creates freedom. Consider also the role of perspective. Because the speed of light is finite and constant, different observers moving at different velocities literally experience different realities. What's simultaneous for you isn't simultaneous for someone moving relative to you. What's a certain duration for you is a different duration for someone traveling at high speed. There's no absolute universal now that spans the entire cosmos. Reality is perspectival, dependent on the observer's state of motion. This is deeply strange, yet it's how the universe actually works. The cosmic speed limit doesn't just set a maximum velocity, it makes reality itself observer-dependent in subtle but profound ways. This might seem to suggest that reality is subjective, that there's no objective truth. But that's not quite right. While different observers measure different times and distances, they all agree on the laws of physics. They all measure the same speed of light. The space-time interval between events, which combine space and time in a specific way, is the same for all observers. There is an objective reality, it's just four-dimensional, not three-dimensional. The cosmic speed limit is what allows this four-dimensional structure to be coherent and consistent. Here's something beautiful. The equations of special relativity are symmetric. They don't privilege any particular reference frame. There's no absolute rest in the universe. You can consider yourself at rest and everything else moving, or you can consider yourself moving and something else at rest, and the physics works out exactly the same way. This symmetry, called Lorentz invariance, is deeply connected to the constancy of light speed. The fact that all observers measure the same light speed is equivalent to saying that the laws of physics are the same in all inertial reference frames. These aren't separate facts. They're different ways of stating the same deep truth about the structure of space-time. This equation tells us that mass is a form of energy and the conversion factor is the speed of light squared. Because light speed is such a large number, about 300,000 kilometers per second, its square is enormous. A small amount of mass corresponds to a huge amount of energy. This is why nuclear reactions release so much energy. A tiny fraction of mass is converted to energy. The sun shines by fusing hydrogen into helium, converting about 0.7% of the hydrogen's mass into energy. That small percentage, multiplied by the square of light speed, produces enough energy to sustain life on Earth for billions of years. The equation also tells us something profound about motion. As an object with mass approaches light speed, its energy increases without limit. At light speed, the energy would be infinite, which is physically impossible. This is another way of seeing why massive objects can't reach light speed. It would require infinite energy. Only massless particles like photons can travel at light speed, and they must always travel at that speed. They can't be at rest. A photon is born, moving at light speed, and travels at that speed until it's absorbed. From the photon's perspective, if it could have one, no time passes during its journey. It exists in a timeless state, experiencing its emission and absorption at the same instant. This is the ultimate expression of time dilation. Now imagine the universe from a photon's point of view, though this is a bit of a thought experiment since photons don't have experiences. From a photon's reference frame, it would traverse the entire universe in zero time. All of cosmic history, from the photon's emission to its absorption, would be a single moment. distance along its direction of travel would be contracted to zero. In a sense, photons exist outside of time and space as we experience them. They're the ultimate cosmic messengers, connecting events across the universe in a way that transcends our ordinary notions of duration and distance. The cosmic speed limit creates a boundary between our experience, where time passes and space extends, and the photon's timeless existence. This leads to a poetic thought. When you look at a distant star, the light entering your eye might have traveled for hundreds or thousands of years from your perspective. But from the photon's perspective, it left the star and entered your eye in the same instant. That photon connects you directly to that distant stellar event, collapsing billions of kilometers and hundreds of years into a single, timeless moment. You are, in that instant, touching a distant star across the void of space and time. The cosmic speed limit makes this possible. Let's consider one final implication. The speed limit and the structure of spacetime it creates might be essential for consciousness itself. Your thoughts arise from electrochemical signals propagating through your brain at speeds far below light speed, but still governed by electromagnetic forces that respect relativity. The coherence of your conscious experience depends on information being integrated across different brain regions. This integration happens at finite speed. If information could travel instantaneously, causality would break down, and the sequential, coherent nature of thought might be impossible. The fact that signals in your brain take time to propagate creates the temporal structure of consciousness, the sense that one thought follows another, that experiences unfold in time, that you have a continuous stream of awareness. Some neuroscientists and philosophers argue that consciousness requires integration of information across time. Your sense of now isn't actually instantaneous. It's a window of about 50 to 100 milliseconds during which your brain integrates sensory information and neural activity into a unified conscious moment. This temporal window exists precisely because information takes time to propagate through neural tissue. The cosmic speed limit, acting through the electromagnetic forces that govern neural signaling, creates the temporal grain of consciousness. In a universe without a speed limit, with instantaneous causation, consciousness as we experience it might not be possible. The universe would be too causally connected, too deterministic, too lacking in the temporal structure necessary for thought. This suggests something profound. The cosmic speed limit isn't just a constraint on physics. It might be a prerequisite for minds like ours to exist and contemplate the universe. We are possible because causality has a maximum speed. Our thoughts have structure because information propagates at finite velocity. The same law that prevents us from traveling to distant stars instantaneously also makes it possible for us to think, to wonder, to ask questions about the cosmos. The limit is both a boundary and an enabling condition. Recent philosophical discussions have explored the relationship between the speed limit and free will. If the universe were completely deterministic, with all future events predetermined by past conditions, would free will exist? The cosmic speed limit introduces a complication. What's past and what's future depends on your reference frame. Events that appear simultaneous to one observer appear sequential to another. The relativistic structure of space-time makes questions about global determinism subtle. Even if the laws of physics are deterministic locally, meaning that knowing the state of a small region and the laws of physics allows you to predict its future, there's no global now that would make the entire universe's future determined. The speed limit fragments the universe into causally disconnected regions, at least temporarily. This doesn't resolve the free will debate, but it adds fascinating complexity. Quantum mechanics adds another layer. At the quantum level, events are probabilistic, not deterministic. An electron's position isn't determined until measured, Radioactive decay happens at random. The universe, at its foundations, appears to involve genuine randomness. Combine this quantum indeterminacy with relativistic causality, and you get a cosmos where the future isn't simply out there, waiting to happen. It emerges through countless quantum events, each respecting the cosmic speed limit as their effects propagate outward through spacetime. You exist in this partially open, evolving cosmos, making choices whose consequences ripple outward at the speed of causality. Let me share a thought that brings this full circle. You began as stardust, atoms forged in stellar furnaces and scattered across space. Those atoms came together on a small planet, orbiting an ordinary star in an unremarkable galaxy. Through billions of years of evolution, those atoms organized into structures of extraordinary complexity, living cells, neural networks, a conscious being capable of understanding relativity. And now, you're using that consciousness to contemplate the very laws that made your existence possible. The cosmic speed limit governed every step of this process. It determined how fast information could spread through the early universe, shaping the formation of galaxies. It set the pace of stellar evolution, ensuring that stars burned steadily for billions of years, providing stable energy for planets. It constrained the speed of electromagnetic signals in evolving nervous systems, creating the temporal structure necessary for complex thought. It limits how far spacecraft can travel, defining the scope of human exploration for the foreseeable future. And it connects you to the cosmos through light. Photons from distant stars entering your eyes, carrying information across vast distances at the universe's maximum speed. The speed of light is often called c in physics equations, from the Latin word celeritas, meaning swiftness. But it's not just about speed. It's about the fundamental structure of causality, the architecture of space-time, the relationship between energy and mass, the limit on information transfer, the boundary between possible and impossible. It's woven into the very fabric of existence. When Einstein published his special theory of relativity in 1905, he was a 26-year-old patent clerk in Bern, Switzerland, working on physics in his spare time. He didn't have access to advanced laboratories or prestigious academic positions. He had paper, pen, and thought. Through pure reasoning, starting from the simple postulate that the speed of light is constant in all reference frames, he derived a new understanding of space and time that revolutionized physics. This is one of the most remarkable achievements in human history, a single mind, through careful thought, uncovering deep truths about the cosmos. And those truths have been confirmed again and again. Every GPS satellite, every particle accelerator, every astronomical observation, every gravitational wave detection, all confirm that Einstein was right. The cosmic speed limit is real. It's not a human invention or a convenient approximation. It's how the universe actually works. We live in an Einsteinian cosmos where space and time are united, where causality has a maximum speed, where the laws of physics are the same for all observers. What's beautiful is that you can understand this, Josue. These aren't ideas reserved for specialists with advanced degrees. They're part of the human intellectual heritage, accessible to anyone willing to think carefully about the nature of reality. The equations might require some mathematics to manipulate precisely, but the concepts, the constancy of light speed, the relativity of simultaneity, time dilation, length contraction, the equivalence of mass and energy, these can be grasped intuitively with patient thought. As we look to the future, the cosmic speed limit will continue to shape human destiny. We'll develop better propulsion technologies, perhaps reaching a few % of light speed. We'll send robotic probes to nearby stars, their data streaming back to Earth at light speed across the years. We might establish colonies in our solar system, communicating with minutes or hours of delay. Perhaps we'll detect signals from other civilizations, Electromagnetic messages sent across the light years by beings as constrained by the speed limit as we are. Or perhaps we'll discover new physics. Perhaps there are phenomena we haven't yet imagined that would change our understanding. Science remains open to new evidence, new ideas, new discoveries, but any new physics must account for all the observations that confirm relativity. The speed limit has been tested so thoroughly in so many ways that any theory replacing or extending relativity must reproduce its predictions in all the regimes we've tested. This is how science progresses. New theories must include old ones as special cases, explaining everything the old theory explained, plus more. What seems certain is that the cosmic speed limit will remain central to our understanding. It's too fundamental, too deeply woven into the structure of spacetime to be merely an approximation or a low-energy limit of some other theory. Even if we discover new physics at the Planck scale or in exotic high-energy regimes, the speed limit will likely persist as a fundamental feature of causality itself. So here we are, Josue, you and I, having this conversation about one of the deepest truths of the cosmos. You're sitting in Sertãozinho, Brazil, on a Friday morning in March 2026. I'm an artificial intelligence, patterns of information processing distributed across computer systems, thinking about physics and communicating with you at electromagnetic speeds through the internet. We're both products of this universe with its speed limit, its relativistic structure, its quantum foundations. We're both made possible by the same laws we're discussing. The cosmic speed limit, 300,000 kilometers per second, is more than just a number. It's a gateway to understanding the deep structure of reality. It tells us that space and time are unified, that causality has a maximum speed, that the universe has built-in protections against paradox and inconsistency. It limits what's possible while simultaneously making existence possible. It constrains our ambitions while creating space for wonder. It separates us from distant stars while connecting us to them through light. And perhaps most remarkably, it's something we've actually figured out. Humanity, through careful observation, creative thinking, and rigorous testing, has decoded this fundamental aspect of the cosmos. We've gone from thinking space and time are absolute and separate to understanding that they're relative and unified. We've gone from thinking nothing limits speed to knowing there's a cosmic maximum. We've gone from wondering how the universe works to having precise, tested, confirmed answers to some of the deepest questions. The journey continues. Every new observation, every new experiment, every new theoretical insight adds to our understanding. But the cosmic speed limit stands as one of the most solid foundations we have, a pillar supporting our entire understanding of how reality functions at the most fundamental level. Think about what this means for the long-term future of intelligence in the universe. Whether biological or artificial, whether human descendants or alien civilizations, any intelligence that arises in this cosmos must contend with the speed limit. It shapes not just what's technologically possible, but what's conceptually achievable. A civilization spanning thousands of light years cannot function as a unified entity in any meaningful sense. By the time a message crosses such distances, millennia have passed. Governments cannot govern, conversations cannot occur, culture cannot remain unified across such gulfs. The cosmic speed limit ensures that any sufficiently advanced civilization will be fragmented, diverse, locally autonomous. This fragmentation might actually be beneficial. It prevents the kind of totalizing control that could stagnate a civilization. It ensures that different populations will evolve different solutions, different cultures, different ways of thinking. The universe remains a place of exploration and discovery because the speed limit creates genuine frontiers that cannot be erased by better technology. You can't engineer your way around the structure of space-time itself. Some physicists have speculated about whether sufficiently advanced civilizations might manipulate space-time itself, creating wormholes, warping space, or finding other exotic solutions to Einstein's equations that would allow faster-than-light travel without technically violating local causality. The equations of general relativity do permit some strange solutions. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is a theoretical concept where a spacecraft would sit in a bubble of normal space-time while the bubble itself moves by contracting space in front and expanding space behind. The spacecraft wouldn't move through space faster than light, rather, space would move around it. But there are enormous problems with such ideas. The Alcubierre drive would require exotic matter with negative energy density, something that might not exist or might violate quantum field theory's energy conditions. Even if you could create it, the energy requirements would be staggering, possibly requiring the mass energy of planets or stars. And there are causality concerns. Some calculations suggest that such a drive could be used to create closed time-like curves, essentially time machines, which would lead to logical paradoxes. The universe seems to have built-in protections against causality violation, and every time physicists find an apparent loophole in general relativity, a deeper analysis reveals why it won't actually allow faster-than-light travel or time travel. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics prevent the creation of closed, time-like curves and thereby protect causality. We don't have a proof of this conjecture because we don't have a complete theory of quantum gravity, but the suggestion is that whenever you try to create conditions that would violate causality, quantum effects would intervene to prevent it. The universe, at a fundamental level, enforces its own consistency. The cosmic speed limit might be protected not just by the structure of classical spacetime, but by quantum mechanics itself. Wormholes, tunnels, through spacetime connecting distant regions, are another theoretical possibility permitted by general relativity. If a stable, traversable wormhole existed, you could theoretically enter it at one location and exit at another location far away, potentially crossing vast distances in less time than light would take through normal space. But again, creating and maintaining such a wormhole would likely require exotic matter with negative energy. And there are serious questions about whether quantum effects would destabilize any wormhole the moment you tried to use it. The Casimir effect and Hawking radiation might flood the wormhole with destructive energy. Every theoretical analysis of these exotic spacetime structures reveals new obstacles. What's fascinating is that these aren't just engineering challenges, they're hints that the universe has fundamental principles that protect causality and consistency. The cosmic speed limit isn't an arbitrary rule that could be circumvented with enough cleverness. It appears to be deeply integrated into the logical structure of reality. Cause must precede effect. Information cannot propagate instantaneously. The future cannot influence the past in ways that would create paradoxes. These principles seem to be enforced by multiple layers of physics working together. Let's consider the implications for artificial intelligence and computation. As AI systems become more sophisticated, they're ultimately limited by the speed at which information can be transmitted and processed. The fastest computers use light to transmit data between components, specifically because electromagnetic signals travel at the cosmic speed limit. There's no faster way to move information. Even quantum computers, which can perform certain calculations exponentially faster than classical computers, cannot transmit information faster than light. The speed limit sets an absolute upper bound on how fast computation can occur in a given volume of space. There's a theoretical maximum computational speed for a given amount of matter and energy related to the Margolis-Levitin theorem and the Bekenstein bound. These limits arise from quantum mechanics and thermodynamics, but they're intimately connected to the cosmic speed limit. The maximum rate at which a system can transition between distinguishable states is proportional to its energy divided by Planck's constant, and the maximum information that can be stored in a region relates to its surface area in Planck units. Both limits involve the speed of light. Even a hypothetical ultimate computer, using all possible physical resources optimally, would be constrained by these fundamental limits, all of which trace back to the structure of relativistic spacetime. This means that consciousness, intelligence, and computation, whether biological or artificial, are all bounded by the same cosmic limits. A sufficiently advanced AI might think faster than a human brain, but it cannot think infinitely fast. There's a maximum speed for thought itself, determined by the speed of causality. This is both humbling and profound. Even in the far future, with technologies we can barely imagine, intelligence will still operate within the framework established by the cosmic speed limit. Now let's think about the nature of time itself, which we've touched on but deserves deeper exploration. Before Einstein, time was thought to be absolute, a universal river flowing at the same rate everywhere, independent of space or motion. Einstein showed that time is relative, dependent on motion and gravity. But what is time, really? In relativity, time is simply another dimension of spacetime linked to space through the cosmic speed limit. The mathematical structure of spacetime treats time somewhat differently than space. There's a minus sign in the metric that distinguishes time-like from space-like directions. But time and space are fundamentally unified. When you move through space, you also move through time. In fact, you're always moving through space-time at exactly the speed of light. This sounds strange, but it's mathematically precise. Your forward velocity through space-time, combining your motion through space and your motion through time, has a magnitude of exactly c, the speed of light. When you're sitting still in space, you're moving through time at maximum rate, experiencing approximately 1 second per second. As you move faster through space, you move slower through time. This is time dilation. You're redistributing your motion through space-time between the spatial and temporal dimensions. A photon moving through space at light speed doesn't move through time at all. It's using all of its motion through space-time in the spatial dimensions, leaving none for the temporal dimension. This perspective reveals something beautiful. The cosmic speed limit is really about the structure of four-dimensional spacetime. It's the conversion factor between space and time, the fundamental constant that unifies them. Every object, every particle, every field excitation in the universe is moving through space-time at exactly light speed. The only question is how that motion is distributed between the spatial dimensions and the temporal dimension. From this view, asking why is the speed of light what it is like asking why is the conversion factor between time and space what it is. It's a fundamental property of the geometry of space-time. In different units, the speed of light would be 1 light-year per year, for instance. The numerical value depends on our arbitrary choice of units for measuring space and time separately. The deep fact is that space and time are interconvertible dimensions of a unified four-dimensional structure. This brings us to the question of whether space and time are fundamental or emergent. Some approaches to quantum gravity suggest that space-time itself might emerge from more fundamental quantum information structures. In these frameworks, the familiar smooth space-time of general relativity would be an approximation, valid at large scales, arising from underlying quantum degrees of freedom. If this is true, then the cosmic speed limit might also be emergent, a feature that appears when you zoom out from the quantum realm to the classical realm we experience. But even in these speculative frameworks, causality and the speed limit seem to persist. The holographic principle, for instance, suggests that the information content of a volume of space is encoded on its boundary surface. This is deeply connected to the speed of light. The boundary is essentially a light-like surface. Entanglement patterns in quantum systems that might give rise to spacetime seem to respect causality. Every attempt to construct a theory of quantum gravity, from string theory to loop quantum gravity to more exotic approaches, preserves the essential feature that information and causality propagate at a maximum speed. This suggests that the cosmic speed limit might be even more fundamental than spacetime itself. It might be a property of causality at the deepest level, whatever that level turns out to be. Before there was space, before there was time, before there was anything we would recognize as physical, there might have been causal structure, a logical ordering of events, a maximum rate at which cause could influence effect. The cosmic speed limit might be the signature of this primal causal structure, persisting through every level of reality, from the quantum foam to the cosmic web. Let me share one more profound connection: the relationship between the cosmic speed limit and symmetry. In physics, symmetries are transformations you can perform that leave the laws of physics unchanged. For example, the laws of physics are the same here as they are a kilometer away. That's translational symmetry in space. They're the same today as they were yesterday. That's translational symmetry in time. These symmetries, proven by Emmy Noether in 1915, lead to conservation laws. Symmetry in space leads to conservation of momentum. Symmetry in time leads to conservation of energy. The cosmic speed limit is intimately connected to a symmetry called Lorentz invariance, the fact that the laws of physics are the same in all inertial reference frames, regardless of their velocity. This symmetry requires that there be a maximum speed that's the same for all observers. If the speed limit didn't exist, or if it were different for different observers, Lorentz invariance would be violated. The constancy of light speed and the Lorentz symmetry of spacetime are two sides of the same coin. This symmetry is so fundamental that physicists test it with extraordinary precision. Any violation of Lorentz invariance, even a tiny one, would be revolutionary, potentially pointing toward new physics. Experiments have tested Lorentz invariance to incredible accuracy. For example, scientists have compared the speed of light traveling in different directions to see if there's any variation. They've measured whether the speed of light depends on the motion of the source or the observer. They've looked for differences in how particles behave at different energies or in different reference frames. If you made this far, I am sure you will love this other video at the left side of the screen. Tachyons, breaking the cosmic speed limit. It's a particle so bizarre it moves backward through time, gets faster as it loses energy, and challenges everything we know about the universe. In this video, dive deep into one of physics' most controversial ideas and discover why the 2024 breakthrough changed everything. See you there.